嗯，
已解锁，请启出话筒。
嗯 Okay, welcome back. So continue with the lifting criteria. Testing. Okay. So last time we discussed that we can lift path, we can lift homotopy, and they are unique. So today we're gonna prove we will lift any continuous map, okay, or base continuous map. So what do I mean by that? So let's say you have a covering map. Okay, so remember that covering map just says that it's surjective first of all, and then every point actually have the same number of pre-image, okay? And at every point you can find an open neighborhood, okay, around the point such that the pre-image is disjoint, okay, and every disjoint part is homeomorphic to the original space. Okay. Then let's say we have a continuous map, okay, from another space into the base space. Okay, so bottom here is the base space. Okay. Then so when we write like this, right, actually we require x naught to send to s naught here. So similarly, on the covering map, covering space map, we also want to send s naught prime to s naught. So the question is, when do we have this leaf here? Okay, such that this diagram will commute. So f ef ef equals to, sorry, f equals to pf theta, like that. Okay, when do we have this? So this happen if only if the induced map of f on the pi 1 of y naught will stay inside the pi p star of pi 1 of. Okay. So meaning this f will map loops. Okay. This leaf will map the loops inside of pi 1 of fy into sorry. So this f here, this small f here will map the loops inside y to a loop inside x, which is a image of pizza. So meaning what? Meaning the image of loops of y, right, can be lifted. It should be lifted. So if you can lift all the loops, then you can lift every point. Right? This is the point here. Make sense or not? So if you can lift loops, then you can lift every point. Okay, so let's define how to lift the points. Well, I mean, before that, I think one direction is easy, right? So which direction is easy? Which direction is easy? Left to right. Okay, left to right is easy. Why? If you know that f is equal to p composed with f tilde, right? Then f star tilde, f star is equal to p star on f tilde star. Then p star of something is the image of star. is already equal. It's not just a subset, right? So left to right is easier by the induced homomorphism. Okay, so maybe induced homomorphism is a fancy word, but really the induced homomorphism is just uh, treating what? Instead of looking points, you're looking at loops at once, right? You look at the points that form a loops. Okay, really it's just mapping points to point. Okay, induced morphism is the fancy word. It's just that we change our core domain to loop space. Okay, instead of point set. Point set. Okay, how about the other direction? So if you have this kind of condition of f, so we wish to define the f tilde. Okay, we wish to define a f tilde. So let y in y. Okay, so what we're gonna do is we use path to define the pre-image, sorry, the lift of a point. Okay, so let y in y, and we will connect this point here. Okay, maybe let's draw it. Don't need to write so many words. So let's say we have a y here. Okay, and remember that our base space is y naught. So let's have a path from y naught to y. So this is gamma. Okay. Well, so if you apply f, right? Okay. So if you apply f, what do you get? You get something like f y naught, okay, which is s naught, and this path become f on y, f on gamma, and then f y here. Okay, we don't know what is fy, but some point in x. So this thing here happen in the top here is y space, bottom here is x space here. So how are we gonna lift? So we claim that there exists a we claim that there exists a unique lift of f gamma tilde. Let's starting at that's not okay by the unique path lifting property on covering space. But do you see a problem here or not? Do you see a problem here? Or see problem here? Okay. Now we haven't see problem here because I haven't defined things. So let's define first. So we're gonna define our lift on y by f tilde, f gamma tilde at 1. Okay, because this is the endpoint of our path, right? Okay, endpoint of our path. Hello. Okay, endpoint of our path. Make sense or not? Okay. Yeah. Okay, 一大早没有力。Uh, should I prove to you that this P on F tilde is just Y? Prove this to you. Maybe I prove it to you why P on F tilde Y is Y. Okay, so if I define like this, right? If I define like this, so Y, F of Y equals to P F tilde. Okay, on the other hand, Y is this true? Sorry? Huh? 哪一个 Which one? 就这边吧。Why is this true? Why is this true? I think we should answer that P inverse of Fy. Does it contain F tilde as well? This is true, right? This is true, right? Because this is a covering space definition. True. So if you look at Fy is a point X, and look at the P inverse, okay, and F gamma is a lift. Okay, so this is a property of this lift here. Okay, this is the property of this lift, and then it is a unique lift. Okay, so it becomes equal. So there's one thing inside there. Okay. What is F gamma tilde? So gamma is a path. So F gamma is another path in it. So gamma is a path in Y. F gamma is a path in X. So we lift this path. Okay. Yeah. I think this follows from the path lifting property. Okay. So follow thing. Okay. But the problem here is we choose a path here. So yeah, it's a point. F gamma 1 is a point. So it's a you lead the path to the lead to a path, right? So you evaluate at 1. So it's an endpoint. That is where our Y is, right? Because our gamma start from Y not to Y. Yeah. Okay. Right. So we leave the endpoint. Okay. So yeah, but the problem here is this gamma is chosen. So we need to show that it is well defined. Okay, so we need to show that it's well defined. So meaning what if I pick another path instead of gamma? Okay, if I use gamma prime, is F gamma prime tilde evaluate at 1 equals to F gamma tilde evaluate at 1. Okay, but what can you see here? Once I have these two paths, I get a loop. Okay, so this is where we use the loop condition. Okay, so let's see here. So if I produce that triangle again, so for both of these paths, right, I will have leaf as well. Okay, and moreover, they are unique leaf. This one, yeah, this one has two definition, 1 and 2 now. Or rather, I use gamma prime and gamma. Okay. Okay, so not that. If you look at this path here, f gamma prime and the inverse of f gamma. Okay, so this is actually a loop. So this is a loop. H naught at x naught. Okay, this is a loop. Moreover, if you rewrite this, this is actually f on the gamma prime start with gamma. Yeah, so meaning that uh, meaning the homotopy class of this loop is living in the induced image of the induced. Okay. But at the same time, okay, we know that this loop here also is a image coming from a covering space. Okay, so still remember last time we put something on this subgroup here, this image subgroup. What do we prove? This is a homotopy class of loop that base in S naught that have a leaf that base in S naught tilde. Okay, so similarly, we can leave this homotopy class here. Okay, we can leave this homotopy class here. Okay, but the problem here is we are lifting a class of, it's not a single loop. The whole class we lift it. Okay, so there's a class that we lift it. But if you think about the well-definers here, let's say I got another H1, okay, because this group is also a homotopy class. So if I have H1, H2, sorry, H0, okay, so inside here maybe got H0, H1, right? Okay, and then there has a homotopy between them, okay. All of these, we can link to the S tilde as well. Okay, we can link this to S tilde as well. So is it okay? For this direction better. Which direction better? Maybe going up better. Hold on. Okay. And if this homotopy is like HT here, we can also leave this HT. And actually they are unique. Okay. Oh, sorry. H1 tilde. But the point is, actually, we just look at this H naught tilde is enough, okay? Since we know all these homotopy stuff already. So the point here is, what is H naught tilde here? Okay, the point here is H F prime tilde 1, okay? So this would, not this, this would imply H naught, H prime tilde 1. So it's still a loop, okay? So this is a loop in the Y state, right? But after you leave, it's still a loop, okay? So at the connecting point, okay, F prime, F gamma prime tilde here, 1 actually is equals to the F gamma tilde 1. Okay, so to complete this diagram here, okay. So actually you have a loop downstairs, you lift upstairs, still a loop. So this homotopy will say that no matter how you homotop, okay, you will always homotop back to this original lift here. Okay, this is the first uh, first way we lift H naught. Okay, all the rest you can homotop to this link. Okay, to make sure that this always hold. Okay, doesn't depend on what H I you linked up. Does it make sense? because now we are dealing with equivalent cluster space, so there's some well-definers you need to take. Okay, because you see this link here is based on representative one, but the problem here is don't care because we have a unique homotopy to back to the original hash not tilde, and then the hash not tilde is the obvious connecting point that connect this f y tilde that we define. Then they connect at f y tilde. Yes. Huh? This one you mean this two? Yeah. We only check for one. Because this okay, because the point of us that we want to check is we want to have well-definers here. You get what I mean? So there are two ways to define it now, right? So this is defined by f gamma prime tilde at 1 or f gamma tilde 1. Okay. So the point here is we want to show that these two is the don't need to check this anymore because this lift is like kind of fixed by covering space already. Why? You must start there. Yeah, but endpoint not sure where. Not sure where is that. Yeah, but because it's a loop, so definitely the point that join they have to like join at the same point. Yes. Okay. You mean gamma of gamma? I think the point is this H1 again. Is this H1? Because instead of lifting to H0 point, you also can lift to H1 tilde, right? Yeah. But the point is we cannot control on H1 tilde. We only has control on H not tilde because we know how we build our H naught. And the H naught has this lift. This lift is unique, so must satisfy. So I can make all the lift homotopic to this lift, and then I know what happened to this lift. Again, this is always true. Okay, question? Got question? Yep. Why the condition are connected and path connected and locally path connected? Okay, good. So whatever we lift here is will be using path connectedness, and then I think continuity will use. Wait, let me see. Yeah, continuity will use path connected criteria as well. But we won't do continuity proof here because it's a general topology type of argument. You can try and read. Yeah. Uh, because when they do that, when they show the continuity, they use open neighborhood. Yeah. So open neighborhood is path connected, so it's pretty important. So the remark that make in notes was the local path connected assumption on Y is very important. Otherwise, lifting criterion could fail. Okay. Yeah. So you can come up with a counter example. Okay, any other question? Any other question? Any other question? Feel free to ask. Not expecting you to learn or understand everything on the spot, but maybe question is very valuable. Okay. Okay. So next is f is continuous. So this one is just like GT. Okay, so we leave it GT kind of argument. So you can try and read yourself. Okay. Next is about uniqueness. We won't prove also is using previously what we have done. So if f1 tilde F2 tilde agree at one point of Y, and Y is connected. So on the connected component, the leaf will agree. Okay, on connected component, that's the same. Okay. So we have done it for homotopy, for path, and then for continuous map. They are the same actually. I think this one is the most general one. Yep. Yes. In this class, most on every map is continuous. Yeah, I think I miss it. You can write continuous thing. Yeah. Some of the book treatment they just throw away continuous map. I mean continuous because all the map we consider are continuous. Hmm. Huh? Space? Space, yeah, space, yes. Because really we're just considering topological space. Yeah. So they throw both these two words away. And topological. Yeah. Okay, actually they refer to topological space. Okay. Okay, so we are good with here already. So next, we will talk about classification of covering space. I think some of you took A2 here, right? And hopefully can remind you of the structure of Galois stuff. Okay, so here's the motivation. So let's just look at the connected covering space of X. So the point here is there's a Galois correspondent from here to the subgroup of X. Okay, this one we sort of see last week already. Okay, regarding for the quiz this week, I haven't come up with a tutorial yet, so you just revise on last week lecture notes. This week, this week hanging assignment already, man. I thought next week. Is it this week? Next week or this week?
This week.
What, this week or next week?
This week.
This week? Oh, I thought it's next week. I'm not sure I'm enough time to finish or not. So let's see what's my question. I don't know I got enough time to finish or not. You guys finish already, man, assignment?
Of course, no.
Yeah, you guys. Simply connected.
Yes, possible.
And you can finish this week, man? Huh? Try. I think supposedly can, because I don't give you covering space now. So you want quiz this week or assignment this week? Huh? You want quiz this week or assignment this week?啊，assignment，你要 assignment，你要做完 assignment 这个星期，是吧？6号这个拜四啊，是吧？你要 assignment，金圣讲要 assignment 啊，其他人讲 assignment 呢，像这个礼拜就没有 quiz 哦 OK 啊，I think 没有 covering space 的是可以做到 I guess 就 cell structure 吧，cell complex。有一个是上个礼拜那样的东西哦，那个 X1 question assignment 还是 quiz 我看你们啊。
对吧？这样
OK，so assignment 就这个拜二，
accept
这个拜二，OK，会啥？上个礼拜的 lecture note 吧。OK，那金盛跟 Eric 不啦，Larry 交上你们的那个 revision 功课，这个礼拜啊，今天，今天啊，今天本来应该是那个 Ivan 的 deadline 是吗？Ivan 还是这里？I think he's okay，应该是是什么？可以帮忙 list 下来一下吗？啊，这周是谁打了啊？到谁了？这周是哎，你的出席率比 Ivan 要高哎，你要不要代替 Ivan 来？这周是谁啊？check 一下，帮我 list 一下他们的 deadline，帮忙提醒一下。我要跟那个汉辉说一下，
那我一个金色换了是吗？
对，然后我要跟他说一说。
然后矮的有没有汉伟换了是不是？
没有，Ivan 没有换，Ivan 就他自己那种，只有汉威跟那个精神换。OK，下一个是 Ehan 啊，this week，Ehan you have to type 啊。
这就不打。
上周是 week 5，这个六了，已经要过大半个月了
6啊，
，week 6了，我们又要过年了。
过年那应该
是诶，你们过年要 intern 呢，哎，很快耶。OK，这样的话我们就考 quiz 下个拜二啊，这个礼拜是一行的啊。OK。Okay, so the Galois correspondence will tell you that on one side, subgroup where the subgroup getting smaller and covering space here getting larger. So what's the idea of getting larger here is the larger space, the kind of larger covering space will cover the smaller covering space, okay, and also cover the base space. So the slogan here is thing we're going to prove here is every subgroup of pi 1 of x prime can be realized, okay, can be realized as pi star p star of pi 1 of x cubed. Okay, so meaning there is a covering space to realize every subgroup of pi 1 cubed. Ask by who? No, how is asking like what did you ask? 是咩？
讲了一个大部分很多人多成。那我问的不是在这一个，我问的不是在这一个，在这个台湾里，
对你问的是在拍
问的好像是在 CW complex 里面那个 H A C 的时候，能不能用 H C 的，也是同一个东西。
你是问这个吗？
Yeah,
没有印象，
that is CW complex. I think
没有印象啊。
because every group corresponds to one CW.
OK，然后 every group correspond to 一个 CW 的样，然后
I want to show you the CW complex of representation of subgroup.
是，我没有印象啊，我没有印象，再想一下，你再想一下，我没有印象。OK， so so how do we realize this? Actually, we realize this by realize a harder question. Okay, we answer another harder question, and then we will build all the rest from this thing. So the problem here is if you can realize every subgroup, right? Realize the easiest subgroup first. Okay, the easiest subgroup is the trivial subgroup. So can you find a covering space to realize the trivial subgroup. So last time we told you already, like the kind of contractible, every loops is contractible there. Okay, so actually that space is a simply connected, but even better than simply connected. Okay. So since P star is always injective, right? So it's equivalent to ask if X has a simply connected covering space. Okay. So the answer is quite hard. Okay, we will briefly go through the construction. 就是有没有一个 covering space such that pi is P star of pi 1 of X cubed。有没有东西 cover 它 such that 这个 P star is trivial subgroup such that this P star is image of P star is a trivial. Okay. Okay, so to answer this, we need more than simply connected. Okay, so we need more than simply connected. So what we need is called the semi-locally simply connected. And let's see what this means. So semi-locally simply connected. So if for every x in X, again, it's a business of open neighborhood. Okay, it's an open neighborhood such that the inclusion, okay, the inclusion induced map is trivial. Okay, so we don't just want the pi 1 of S tilde is trivial. We want every point have this kind of trivial neighborhood. A neighborhood that gives trivial inclusion here. Okay, so this is actually strong. Okay, this is actually strong. Okay, so one proposition you can try to prove, which we don't want to do in class, is if you have a covering space, which is simply connected, then X is semi-locally simply connected. Okay, so this is one direction. If your space have a simply connected, if your covering space is simply connected, then your base space is semi-locally. Okay. So the whole game is to play another direction. If your base space is semi-locally simply connected, then we can construct a simply connected SQ die. Okay. So can you imagine what is going to happen? This semi-locally simply connected is about neighborhood. So you should think that we have to build our SQ die using a bunch of open neighborhood. Okay. So you patch all the how to say contractible, contractibles open neighborhood together to form your simply connected space. If you still remember our simply connected covering space for S1, where S1, do you still remember the fractal cross, a lot of cross? If you look at around open neighborhood, it's just a interval, which is contractible. So we put a lot of interval together. What do you mean? Can. Open set can overlap. Covering space, right? Open cover, right? Okay. Yeah, so this proof is quite straightforward. I'll just leave it for you to see. Okay, so maybe give you a non-trivial example of not non-trivial, non-example of not locally simply connected space. Okay, so this is a exotic example in analysis. Okay, so what we're doing was we have a bunch of wedge of circle, which getting smaller and smaller. Okay, for example, this is radius 1, this is radius half, 1/3, 1/4, like that. Okay, so can you see why is this not semi-locally simply connected? So meaning, can you find a point, okay, such that every open neighborhood around it, the inclusion induced map is not trivial. So meaning the pi 1 of that open neighborhood is not trivial. Can you find a point or not on this shrinking wedge of circle, wedge of shrinking circle? So can you find a point, okay, such that every neighborhood you find, the inclusion of your pi 1 is not trivial. So meaning there's non-trivial loop inside your open neighborhood. That's an easy way to see. Can you find a point? Huh? Yeah, wedge point. So if you follow the wedge point, you build an open neighborhood by Archimedean property, you will find a bunch of a bunch of circle inside there. Then you will have non-trivial pi 1. Okay, no? Does it make sense? You come back to Archimedean property. Okay? But not because this is infinite, I'm not stop here, infinite. I cannot draw many. Maybe I draw like this. Okay. Not infinite. Okay. So you can refer to the full argument I write in the notes. But we can make it semi-locally connected. Okay, so there's one way to make it semi-locally connected. Let's call this X. So we consider the cone. Okay, so what about this cone here? If you still remember what's cone. You remember ice cream cone? Easy. Okay, so you just take X cross I and then portion out one side. This is contractible already. Why? You have a bunch of this infinite wedge circle, right? And then you hide out on one side. Okay, and then this space is contractible. Okay, so everything can contract to the cone point. Okay, but might not be differentiable. Not differentiable. It's okay. All right. Happy? Good. Okay, so we don't consider this kind of weird space. So next, we're going to construct the simply connected covering space. Maybe we'll talk about construction and then we will break there. So there are three kinds of connectivity we like. So first, path connected. Second, locally path connected. Third, semi-locally simply connected. Okay, this kind of space, only then we can have these simply connected covering space. You might think that it's quite restrictive, but for most of the space we are interested actually satisfy this property. Okay, for most of the space we are interested, at least in this class, will satisfy this property. Okay, so let's build it. We have the following simply connected space. Then later, I think we will justify why this connected. Oh, okay. I think, yeah. Or should we know now? This space actually we should use the. I mean, all the rest are isomorphic. Do we know it now or later? Maybe later. This is actually the simply connected covering space. Okay, so how do we construct this? Let's call it the S tilde head. Okay, this is the head of all covering space. S tilde head. Okay, so very interesting, huh? So we take a homotopy class of a path, okay, that just start from the base point. Okay, the construction is easy, but the proof is very long. Okay, so yeah. Okay, we just take homotopy class to become the element here. So it's an equivalent class. Set of equivalent. Is this well defined? Is this well defined? If I pick different representative here, do they have the same endpoint? B, right? Because this is a homotopy between half, they should have the same endpoint. Different endpoint, there's no homotopy. Okay, only between same endpoint you have homotopy. It's not, you cannot have homotopy from the loop to a path. Okay, unless you are talking about homotopy of continuous map, that one I don't care about endpoint. But if I say homotopy of path, then we care about the endpoint. Homotopy of loops, the endpoint become one point. Okay, so be careful. What kind of homotopy class we are talking about. Okay. So this is well defined. Okay. Yes. 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 That's right. So we're gonna put topology on here. We're gonna put topology here. So later you're gonna see equivalent class of equivalent class. Okay. Can you imagine or not? Equivalent class of equivalent class. Okay. So first is this is well defined. Let's build a topology and then we take a break. So let's build a topology here. How do we define topology? So there are a few things to do here. We will build a topology on S tilde head. Okay, and then you need to show that P is continuous with regard to this topology. Okay, and then you need to show that P is a covering map. And then lastly, we will show that this space is simply connected. Okay, we need to start with topology, only we can start to show continuity. Because X is topological space, we know already, but how do you decide whether the inverse image is open? Okay, so we need to make some proper topology here. So, sorry? Yeah, so we're not gonna write all the details, but I'll tell you the main point. Okay, so how to build topology here? So to build topology, there's few ways, right? So we're gonna use a basis to build here. Okay, so I will tell you what's the basis. That's all. Okay, so what's the basis here? This basis is very fun, huh? So you just take open set in X. Okay, we know how open is on X. So you take open set there. And this open set here has to be path connected. But our space is already path connected. Obviously, this is path connected. And because it is semi-locally simply connected, right? This is the open set we're going to take. Okay, we will take the semi-locally and simply connected open set to be our topology on. Oh, well, before building the topology on X star, right? This is the basis of topology we take on x first. Okay. Then we will consider how to build one for x tilde hat. So this is the basis we're going to take on x. So obviously you need to show that this is a basis. So how to show basis? You check what? Every point, every for every point, every open neighborhood, there is a element in the basis which contain the point and then contain inside the U, right? And then also the intersection also contain one of this kind of neighborhood. Okay, this is what you did. So we skip the GT argument. But it's written in the note. Okay, good. Okay, so you could show that this works. And then how do we build the S prime tilde one? So let's build this one and then we will take a break from here. Okay, so how to build one for S prime F tilde hat now? Well, not that. If you have 2 points inside one of the neighborhood, the basis neighborhood, then there's a path connecting them. Okay, because it's path connected. So and all such path is homotopic. Topic in X because the inclusion is trivial, right? So every path is okay, because the inclusion is trivial. Pi one of U is trivial. So in this case, given a homotopic class of path in a simply connected space here, and a U, this special U here, the neighborhood coming from the semi-locally connected condition, such that gamma 1 is in U, okay. This one makes sense because y is in U. Okay, so gamma 1 is in U. So we're gonna define the pair here, gamma U. Okay. So what's gamma U here? Very important. This is a very interesting construction here. So what is gamma U here? So gamma U is all the path, all the homotopic class in X tilde, with S tilde hat, right? Okay. Such that this homotopic class here is equals to the homotopic class of gamma composed with eta. So what's eta here? So the eta here is just any other path inside U. Okay, such that it starts with the endpoint of gamma 1. So you can think of like the spider web. This is a spider web. This is a spider web that starts with gamma. Okay, so let me draw something here. Maybe your U looks like this, right? Okay, and then gamma maybe here. Okay, here is a gamma 1. So you take all the eta, maybe eta 1, eta 2, all of these. All these lines live in one basis. Okay. Or you can think of it like a blood vessel here. Within this U, where if there's a path that connects to this gamma, I just connect them together. I collect them together. Then we claim that this is a basis for S tilde hat. So you need to go through the basis argument again. The intersection, everything. Okay. Happy? Okay. Any question? Maybe we can stop here first and then we can discuss What more to discuss here? Hmm. Okay, maybe we'll discuss simply connected. Continuity, we also skip it because it's a GT type of argument as well. You need to show the pre-inverse is open stuff. 什么？有点什么？放心，一行啊，Yeah，OK，没有问题啊，没问题。Okay, then let's break until 10:00.
Yeah.
还有其他课？
什么 DM？不算框完了，可能1个小时才来。
What do you mean by use A4 paper next time?
大一点的词啊，看你都不够写，就是你才写差不多2、3行就要跳去下一页了。
没有啊，就是因为我本子就要顺着写下来的时候就
对呀、就不够嘛。如果你放 A4，怎么会跳到下一页呢？你懂什么意思？
不管有多大的纸都有可能会跳到下面。
但是也太快跳了啊，我才看不到几行已经跳下一页。有那种 full sketch 吗？你知道吗？你知道 full sketch 吗？就 A4，然后它有一行一行一行一行一行一行，有那种。因为现在的 argument 比较冗长啊，不能给你这样2、3句就写完了，所以我答案还没有 post 吗？我回去 post，
看到你 post 了，
我回去 post 那个 assignment 答案。那个有问题啊？你觉得？
你感觉就是讲不能用这个，
是没？
你们讨论。
所以你的
我忘记了哈，
你的 assignment 的选择 actually
30吧。
没有，他没有写，没有。
他写吗？
你跟我讲我可以用，可是我要写，我要跟你讲那个我都可以讲。
你再量写吗？你去知道，不然自罚一本。去写一下量写。
前面我已经做到很 obvious，开始对。
超有。对。
你真实决定的时候就看得出了。
我看不出来。
只有的 assignment
你自己看出来噻。Yeah，I mean 你们的 assignment 我觉得你们 OK，大致。
只有的 assignment 难度
呀
太小小，
哎，今天是
重点是他自己都没有做过，
他没有做过，他会有答案出来吗？
反正一堆 typo，然后去找他的时候，他说他自己都没有做过，
是哦。
他随便挖题目出来。
对，
他马上有做过了。
有啊，这个我做过啊，这个我做过。
这是不是最近做的？我猜，
反正都是最近做，之前。
他们的第3题啊，他讲让我们跟那个 S1 Smash S1 是写错了，是
是
Wedge，
为啥还是 F？
因为
你看一下那个
因为这个就是 S2 来的嘛，就不需要写成这样子。
你看这 hatcher 里面是我打错吗？因为有时候 V 打到 Wedge，它会是往线。 这是 actual 的，你看一下有没有打错，
可以可以。
不然我贴一下，等一下。
我记得你说这个，
每个考试前2个，什么？
那 project 是哪时候开始？
可以开始啊，你可以开始啊，可以开始。
对，还要给
我题目全部 list 在那个里面，
地权啊，
地权。那你看课本里面那种，他叫你去读 paper 那种，就可以变成你的题。
可以选后面一点。
做不可以啊，
到后面的地方后面。
可以啊，可以选后面一点。我连第一课都还没有讲完呢。
看出来。你在说什么 project recommendations？那是 project。
有吗 ？Which 啊？V
啊，
是 V 哈。OK OK，我回去改。很少会用到那个 Smash 哦，至少了目前。
这个呢？
就是你 list 的这个是 project。
对啊，怎么？
不是给 master。
你们也是一样
我们也是这个 list。
啊？你们也是从这个里？
那就 chapter
什么？要 report， 要，因为 assignment 减少嘛，就变成一个 research paper report。
你是懒惰改我的，
难道改你的吗？
那个 revision 你给了我3周，是不是应该给我多加点？
可以考虑给什么？看呢？
我不需要给收一点的，拿4.0好吗？
好，很好，非常好，最喜欢你这种学生。我不是我相信你，你要相信你自己。我觉得你们做 assignment 的能力是不用比较没有当心的，只是像你们讲的，可能考试那种要训练一下应急方面，
这样
要练一下应急方面。
我考完了就想到答案了，没办法，要模拟一下。我想，哎，考试完了，然后我就，哦，想要答案，然后你就
让我们一拍下去讲，哦，考试考完了。
哦，我知道答案。
考完了，OK，就开始这样。Fundamental group is isomorphic to 谁的 fundamental group？怎么可能？
我真的有谁
那个是 S1 啊，还有 next one。
啊？对，他
对呀、
对啊。
他是 isomorphic 吧？
I mean like，
我们这个课里不用管它是不是 isomorphic， canonically isomorphic 我们就把它当做等于。
对呀、
我不喜欢嘞。
这样你就 isomorphic 啊，
那你去跟 Justin 聊一个。
你就 isomorphic 啊，但是我们这里就把它当做 Z 来看啊，我们 Z 长那样啊，我们 Z 不是1减1。
然后你 Z 是 Q 的 subset。
不一样啊，S one。
isomorphic 啊，你要吗？我是 accept 你啊，在这个班。
canonically isomorphic we treat it as equal， 除非是那些就是它们 isomorphic， 但是它有不一样的 isomorphic 这种，我们再不写。
所以啊，我问你，如果 A homomorphic B 啦
homeomorphic 跟 isomorphic 不一样吧？
那你 A 和 C 啊怎样？
没有，你讲喂什么？
喂，怎么可能 A
什么
homomorphic to B isomorphic to C？
是 homeo 还是什么？
哎呀，如果 A homomorphic 跟 B 的话，
干嘛？
我们有30 equivalent，
什么叫 A homotopy to B 先
我们有30
？Deformation retreat 哈，还是 retreat 还是
没有，它就是
homotopy equivalent 哈？
对，如果 A 和 B 是 homotopy equivalent，B 和 C 是 homomorphic，这个 notation 会很乱。
不会，因为
啊，因为后面嘛，
homomorphic 就是 homotopy equivalence，
所以如果它是 isomorphic 的话，
isomorphic 没有东西在，会没有，你是怎样的 isomorphic？不是，你现在是在讲 space 上面 space induced isomorphism，homotopy equivalence induced isomorphism 啊，就这样。space 上面的 isomorphic 是什么意思？vector space 的 isomorphic 就不知道了哦，就没有关系哦。
Topological 的话就是 open set to open set，然后是吗？Topological
那个是 homeomorphism 嘛，那个 homeo 咯，那是
如果是
homeomorphism。
homotopic 应该还不用那么强。
哦，都并没有
不是叫 homotopy equivalent，没有那么强啊，但是还是在台湾上面是 isomorphic，
对，
就够了。
就
我们三
相当于三个 equivalence。
什么呀
isomorphism、homotopy equivalence 和那个 set theory 的 equivalence，就是两个全部东西一比
？bijection，
就 bijection，
OK
就等于吧，就普通等于，所以我们有三个等于的。
OK，但是在不同的地方上面。
我要发明过来 notation 啊。
OK，
我们把 homotopic 跟形成等于。
homotopy 是一个
就
线的
是一个咯 ，CMac
isomorphism
CMac
一个这样，然后两个
其实它叫 thin 什么数
经常写
啊，哪个啊？CMEQ 不是 CMac，
我不要讲这样的
OK CMEQ
isomorphism
Sim
thin 上面那
啊，
个
你去看了，
啊，说 Sim stand for 什么？来，它有全名吗？应该有全名不是
大概
？EQ 应该就是 equal 吗？Sim 的全名是什么？对不对？
那个弯就叫 sim。
我知道它叫，那你不叫那条横叫 EQ，那是 equal 嘛？它把它缩写嘛？对，OK，so we'll leave covering map and continuous lah, continuous because these are general topology kind of argument. So let's show simply connected. Because this will use tough stuff to show it. So let's see why the pi one is 0. So there's one observation to make here. For these two GT. Oh, similar. Whoa, similar. Okay. Okay, observation. So there's some observation here. So if gamma from I to X is a half starting X naught, then what's the lift? Huh? Then what's its lift to S gamma star? Okay. So what's this lift here? So just now we just send a homotopy class to a point, right? So 你可以 imagine 什么事情？现在我有很多 point 哦，很多 point 可能是从不同的 path 来哦，然后发生什么事情 ？What happened to this path of leaf? What happened to this leaf of path? So just now, every point, right, come from the endpoint of some path, homotopy class of path. Then now you want to put a bunch of points together and then lift them. You understand what I say? I draw it. So just now we have gamma 1, right? So this is the endpoint of some gamma. But if you have a bunch of points here, maybe this is gamma 1, 1, this is gamma 2, 1, gamma 3, 1, gamma 4, 1, gamma 5, 1. Right. All of these correspond to homotopy class of half. You see what happened or not? You see what happened to the leaf? The leaf is a path of homotopy class of half. Can you see or not? This is a path of homotopy class of half. How are you going to write that down? Huh? How are you going to write that down? Double square bracket. 哎，差不多，是 double square bracket 对。Okay, so let's write it down. Okay, so you can see that the lift of S naught is a constant path. This one makes sense. Okay. So let's write down this path here. So this is a giant path. So this is a double bracket of path. What this path do was you send t to gamma s. Okay, so this s is to show that this is a path in S Theta hat. But every point itself is a moving class of path. Make sense? Make sense?
Oh, still, yeah.
Okay.
Yeah.
Yeah. So 你说，你说。So let us digest this path a bit. Okay, let's digest this path a bit. So this path is equal to gamma from 0 to t. Is this true? And is stationary at the gamma t on t to 1. So let's check. Did I write something weird here? On 0 to t is moving using gamma, and then t to 1 stop at t. Is it right? 看看这句话在干嘛？哪一个？ET 讲 vector stationary 啊。See. Okay, so if you put 0 in, right, where did you start? So if you put 0 in, this is gamma 0. So gamma 0 is just trivial point. Okay. It's just the starting point, which is S naught. But if you put 1 in, you stop at gamma t. So if you put at 1, you stop at gamma t. 有点什么奇怪？
因为它就是你的画风
缩小。
缩小的话，是一个它是能定义它，就是它作为一个不
Yeah. But 这句话是什么啊？忽然间想不起来去。这个 path what is this？为什么放一进就有两去干嘛题？
一层题二题，
对，一整题是题，对。会有问题吗？干嘛题？
类似反的零和分群分类吧，
什么嘞？
怎么了？
为什么
它是一个点嘛。
？Well, I mean like 现在我有点 confused，是这个是属于的东西，是 S 的东西。 假设这个 f 的容题，then 如果我放 t 进去，你真的这个东西就变 t square 了，很奇怪。
你是不是一个零空间？
去确一下出什么钱？
这在干嘛？我写错了。先看我写错了。没有啊，它确实要 end 在，它确实是要 end 这个 part，this part will start at e as not and then stop at gamma t. That's true. Okay, so this is okay, but these two command here is a bit weird. Why I write this?
所以 why
啊？
一点点那我
because why 哈？Because let me think.
零
Because the endpoint of gamma is gamma 1, but the leaf of gamma 1 is gamma. By this construction, you see? Go back to this construction. So the endpoint of gamma is gamma 1, but the leaf of gamma 1 is gamma. So we have to stop at gamma. But what's this two comment? I forgot already. I don't think these two comment come from Hatcher. These two comment from the 1000 patch. What is this? I forget this already. Shit. Why I forget this? Now here. Why stationary? Huh?
why we need another
Okay, why do we need another bracket here? Because S tilde hat is an equivalent classes. Let me think.
It's just the equivalence classes of paths, and then when you has to try to combine the
How do we define? Let me see. Do we need the equivalent class here? Maybe for now we don't need. Later when we consider pi 1, it will become equivalent class. Let me think. We need because do we need? We need because okay, we need it because this is a real function. This is just a real part. So we need a homotopy of it. Yeah, this actually is just a name. This is just a name. Maybe later will be more apparent why these two double bracket make sense. This is just a name, but the real map is this one. This is just a gamma, right? This is just a part. So it's a homotopy of. But later will make sense why we define this map of this. Okay, so later will make more sense when you consider pi 1 of it. Pi 1 of S tilde hat, that for sure you need double bracket, right? Because your element is already a homotopy class, but you consider pi 1 is the equivalent class of equivalent. Okay, so later we'll tell you why this notation makes sense. But for now, it's just a map. It's just a gamma. Okay, but I forget what's this command about. I forget. Can we come back tomorrow? I mean Wednesday. Okay, let's come back Wednesday. I forget this. Seriously forget. Because now also cannot check. Let's not spend time checking this now. Okay. But then we're gonna show that pi 1 is 0. But is path connected obvious here or not? Because from this construction here, we already built a path. So I think I left it for you to show path connectedness. Obvious from construction above because the gamma we pick here is arbitrary. Okay. Next, we will show that the pi1 of x tilde hat, that base at this constant map here is 0. Okay. So it suffices to show that P star of pi1 of x tilde hat is actually 0. Okay, because we know that P star is injective. Okay, once we get this is 0, then the kernel must equals to the trivial group. All right, so how to show this up? How to show this? Right. Because P star is always injective. After we show it's a covering space, then the induced map is always injective. So injective. P star is always injective. Instead of showing pi1 is 0, we show that P star of pi1 is 0 because P star is injective, the kernel must be trivial. Okay. So we just look at the image after applying the projection map, actually covering space map. All right. So element in the image of P star actually are the loops at x naught that lead to a loops at the ex naught. Okay. Okay. But then not that. What happened when x equals to 1? So if we put x equals to 1 inside there, on one side, okay, actually we have to come back to ex naught. But from the calculation above, we also know that this point here is also gamma. Okay. But this says what? But this implies that every loops actually equals to ex. Okay. So this says that gamma is now homotopic. Because these two are the same homotopic class. Okay. So first point here is because we are considering the image of loops. Okay. Second here is just by construction. We can link to any path we like. Okay, then these two together, every path is a loop. Sorry, every path is a constant path. So this just says that gamma is not homotopic. Okay. So this shows that gamma is. Okay, makes sense. A question? Any question? If you look at these two questions, do you know how to make this function look like this two thingy? So this map here have to equal to gamma on the 0 to t, but equal to gamma when s equals to s equals to 1. Stationary at gamma. How come? This kind of means that so meaning if you change the variable here, I'm not sure this is for S or T, I forgot already, but if your some variable run from here to here, you will always start with gamma T. Then it is a constant map like gamma T of the mod S dot also mod S dot. I feel like I messed up with the S and T, so that's why I'm very confused here. Is this S or is this S or is this S? I think I messed up with the S and T, so where should be S? But above one is S, 0 to S. Okay, and then but if 0 to S or why is it equal to gamma? But yeah, or there's something wrong with my math, man. ST. I think I go back and check what's going on here. Okay. Anyway, so there are a few ways to build simply connected space. So maybe simply connected covering space is very hard, but if you know how to build one or two, you can build a third one. Okay, so what do I mean by that? Okay, so if you can build two of them, then you can build the third one. So this is what I mean. So let's say for S1, you know that R is simply connected covering space for it. Then we can build S1, which S1. So actually put a bunch of R together. Okay, so this is exactly how we build the cross. Okay, the fractal, the crossing fractal, right? Okay, so these are a bunch of R, but R is homeomorphic to some open table interval, right? So we just put the interval together. Okay, can think about the covering space like this. So every part of it is like the simply connected covering space for X1. Okay, make sense? Because there are two directions for you to proceed. 那你就上串，这没有三，有四个，只是画成几角吧。这画四个，只是画成几角吧，有点像雪花，雪花飘飘。OK， OK， 四个就是两条线啦。Because one S1 is R, right? The other S1 also R 嘛，so I put these two R together. AB. No. What do you mean by free group generate AB? Don't simply think about free group because we have pi 1 that we're gonna associate free product. I mean, don't simply use the word of free group because group here we usually correspond to fundamental group. But here if you want to talk about fundamental group of this space is trivial. Okay. But the point here is just that we want to use the simply connected covering space that we know for a simpler space to build for a more complicated space. Does it make sense? Does it make sense? So previously, you know that the real number will cover x1, okay? But now you got two real number. Then you need to put the two real line together. Okay, so how you're gonna put this is here, or this is how you're gonna put it. Okay, for this space, for this kind of space. For this particular space. Does it make sense? Question, got question? Yes.
X cube X. Is it all the universal cover?
Yes, later we will define it. Yeah. Okay, later we'll show isomorphism between these covering space, and then we will coin the name for it. Yep. It is a universal covering. Later you will see why it is a universal covering. Okay, so let's go to the Galois correspondent now. So let's say we have a path connected covering space. Okay, and then blah, this is a so first part is the story we have been talking about. Let's say we have another point, okay, in the pre-image, because maybe the number of sheets is a lot, so you can find another pre-image. Then you can take a path between these two pre-image, right? And if you map it down, okay, if you project this gamma down, it will be a path on S0, okay, because both of these are the pre-image of S0. So you project down at the top, maybe it's not a loop, but project down is a loop. This idea is like the monodromy, okay. So if you have seen monodromy before, so at the bottom you have a loops, but when you lift to your fiber space, right, it becomes 2 point. So it sends the pre-image of this loop to another pre-image. So a loop at the base space, right, will have an effect on the pre-image of this base space here, which we call a monodromy. Okay, so this is a loop action. Okay, a loop in the base space have an action on the covering space here, but in a more general sense, it's called a fiber space. How do you think about fiber space? It's just base space have a bunch of pre-image density. Okay. Okay. So then yeah, this one is a loop. Okay, let's continue. Then what we can do was we can conjugate your subgroup by this loop. Okay. So what happens if you conjugate? Okay, if you conjugate, then you change your base. You change your base pointer. This is what we have gone through also last time. Okay, we change the base space. And then what? Then we have these two. Do we have these two? See. So the subgroup. So together, let's see, we obtain the function. Okay, so if you have a base covering maps, then you will get a subgroup of I1. Okay, good. So the first part here is what we have known already. But from the conjugation argument here, if you don't care about base point, then this will just correspond to conjugate C classes of subgroup. Okay. Instead of real subgroup here, you just correspond to conjugate C classes of subgroup. Okay. Does it make sense? Does it make sense of this? Do you make sense of this or not? If we don't care about base point. First one is we fix base point. Second one, we don't care about base point. Okay, if we don't care about base point, you will only get conjugate C class. Okay, meaning maybe you are looking at other x0 prime, x0 prime tilde. Okay, supposedly these are two different subgroups, but if you don't care, then you get either one is okay. Does it make sense? Didier. So if you fix one x naught tilde, then there will be only one subgroup. Okay, but if you look at different x naught tilde, they will correspond to the same group up to conjugate. Make sense? With the loop above. Okay, with the conjugate action above. Okay. If you don't care about S not tilde. Okay, so then we want to show that by taking appropriate equivalence relation, actually these are one-to-one correspondent. Okay, so for now is we got a covering map, we can compute the subgroup. But now we want to say that actually there has a one-to-one correspondent by quotient out enough thing. Okay, so what's the enough thing we need to quotient? So let's look at the surjectivity first. Is it obvious that if I give you a subgroup, you can find this SH tilde? I think it's not obvious. Okay, but we have the simply connected covering space just now. Okay, we're gonna make use of that. Because in that space, right, the loops, there's no relation. There's no relation between them. There's no like any path that compose your identity. So there's no relation. So we're gonna put the relation into that space. Okay, so what we're gonna put is we're gonna say that let's take this simply connected space. We'll say that two path is the same as long as what? As long as they form a loop. They form a loop inside our loop. And because if you're given a H, and this H has to be studied inside as a subgroup of L of X, so you know what's the loop there. Then let's say these two have the same endpoint, then we're gonna concatenate them with one of them transverse backward. Okay. Because they both start at the same point, but we just consider those paths that end at the same point as well, and then they form a loop. Okay, they form a loop, and then this loop live inside H. Obviously, you need to show that this is an equivalence relation. Okay, this is an equivalence relation. Okay, once you show this, then what we're gonna do is we define the new covering space as X tilde hat portion out by this H here. Okay, anything we need to check? What do you think? Do you think anything we need to check? Obviously, we need to check that this is a covering space. Okay, we need to check that this is a covering map. Okay, this one is topology kind of stuff. But the main important thing is really this do the job. Okay, we need to make sure that this really do the job. Okay, this really do the job, meaning the pi one of this S tilde H we produce here really have image as H. Okay, we have to make sure this is true. Otherwise, it's useless. Okay, so this is the thing we need to discuss. So why is this H? Okay, so two directional. Okay, two direction to do. So let's do which direction first. So let's start from right to left. So let's take a path in H. We want to show that it's image of P. Okay, image of PH here. This is a covering map. Okay, so if you are element of H, okay, element of H. So what's H here? Do you still remember? H is just subgroup of pi one of X. Obviously, you can leave it to the simply connected space. Okay, because simply connected space, we already proved that it's a covering map. But then what? But then you are lifting to ES naught, okay, and then N at gamma. Okay, I think this is okay. But the point is, the lift to S tilde H actually ends at these 2 points here. Okay, actually this refer to the EX naught inside your SH tilde Y. Still remember just now how we equate the two paths inside SH tilde. They end at the same point, and then they are composed with one of them transverse backward is an element in H. Okay. Yeah, so is it clear that gamma 1 is ES naught? Is it clear? Gamma 1 is ES naught. Is it clear or not? Gamma 1 is ES naught. Because gamma 1 come from where? Come from H. H come from where? Is pi 1 of X. But pi 1 of X means what? It's a loop. So gamma 1 have to be S naught. Okay, ES naught 1 also S naught. But then if you compose these two together, for example, maybe you can take gamma with ES naught transverse is gamma, right? But gamma is in H. So inside S tilde H, these two are the same part. So same. But same path mean what? Same path means the leaf here, okay, the leaf here inside this SH tilde start at the same point, okay, which means that this gamma tilde is a loop. Okay or not? Does it make sense? There are few equivalent class happening here, so please be careful. Okay. On the other hand, if you are the image of pH, okay, if you are image, then what do you need to show? You need to show that this path here will live in H. Okay, to show that this path is living in H, what do you need to show? You need to show that this path composed with ES naught is again living in H. Okay, this is what you need to show. So how to go to this stage? Oh, so you got a loop in X tilde H such that your image is gamma. Okay, good. This one. Then the leaf gamma tilde here was starting at ES naught and end at gamma. Does this make sense? This makes sense or not? I think this is the construction of our simply connected space, right? So you remember just now the equivalent class of equivalent class. Okay, we start with ES naught and then end with gamma. But the point here is, since this gamma tilde is a loop in SH tilde, okay, it just means that gamma must be ES naught. Okay? Because this equivalent class of X tilde here is a loop in SH tilde. So you need to apply the definition of SH tilde again. Okay. Yeah. So at the end, it just boils down to go back to SH tilde. One is to show it satisfies SH tilde condition. One is to use SH tilde condition. Okay. To see that gamma is just gamma wavelength. And then this thing is in H. Okay. Any question here? Question? Any question? Repeat again. So from here, from where? Sorry, this part, the whole part. Last line. Last line. Okay. So since gamma tilde is a loop in SH tilde, so what does this mean here? Okay, so what does this mean here? So this means here, the starting point and the end point is the same. Okay, the starting point and the ending point is the same. Okay. So same paths mean what then? So how do we use this condition here? So in the end, we want to show that this gamma, because of gamma, live in H. Okay, so why writing this pattern, or why this is equal? Hmm. So how to live in H? How to live in H again? Yeah. So define an equivalent by this is the same. Oh, okay. So if you look at this definition, right, these two are the same if their composite is in H. Okay, composite as a loop, so you need to take transverse on the other loops, other path. So what I have done here is, what have I done here is对刚刚我觉得 yes no。现在我想要想的是，like，前面一句对后面一句有什么帮助？对后面有帮助吗？后面后面如果他们真的一样的话，这个放在一起不是会 cancel 掉吗？
identify with
什么
in an equivalent relation。
啊？
你这个
对
representative
Yeah. I think 你是对的。Yeah, okay. So，也对，
是如果上
所以是 identify as a H 啦，就是下面那句话就对了。可是那个 loop 有什么关系吗？哦，有关系，因为 because it's a loop, so that 我讲一下 loop 有关系吗？
因为
啊，
伽马伽马
嗯哼，
伽马自己是在一个 relation 里，
嗯哼，
跟他们的 product 是 EX 到，所以其实伽马的 classes 里面会有 EX 嘛。我利用那个条件的话，就代表伽马 EX 到 inverse H。
我也再一次，
它不是呃 reflexive 的咩？
对，它是 reflexive，然后，so 现在 OK，现在的 problem 应该是 I cannot say straight away say that gamma 就活在 H 里面吧，对不对？但是我需要靠这个 gamma 跟 EX not inverse to say 的，它是在 H 里面，是这样讲的。Yeah, because because S tilde is a loop in S tilde H. So 这个我看清楚，这样看东西。哦，OK, good，非常好。So if you still remember this S tilde head, right? There's no loops. So whatever loops inside this S tilde head H, this loop is have to come from this. All the loop have to come from here because the simply connected space have no loops. So once you have a loops, meaning this product here will stay inside H. So we need this to tell us something say inside H. So you need a loop. So that's gamma with that E composed together is a loop. Then only then you can say inside here. Okay. Okay, any more question? Okay, basically, this is the construction already. So let's quickly spend 2 more minutes. 借我2分钟. So next, we will talk about this isomorphism here. So isomorphism between covering space, right? Okay, is a homeomorphism. Okay. Isomorphism between covering space is homeomorphism. We use isomorphism here, not homeomorphism. Okay, so be careful. Sometimes isomorphism is just vector space. This is a bit different. Okay, so next you have a base uniqueness here. Okay, so this is some routine to check its unique. And then we get this big classifications theorem here. Okay, so if you have subgroup, you will have a covering space. This is the H we built, the equivalent relation H we built. And then you can use the uniqueness. You can show the uniqueness easily once you have that. So the big work is to build that SH. Okay, after you build the SH, actually uniqueness is quite easy to show. Then if you ignore the base point, then on the right-hand side, from your side, become conjugate C classes of subgroup using the conjugation of loop on both sides. Okay, so uniqueness is not too hard. You can have a look. So the main point is that equivalence relation construction. Okay. Yeah. Okay. So how do we see simply connected space is covering space of for the rest? Sorry. 我学生迟到刚才。Okay, the consequence of the lifting criteria is that a simply connected covering space of a path connected locally path connected space is a covering space for every other path connected covering space. Okay, so this follows from the lifting criteria. Okay, so that's why simply connected covering space of X is a universal cover. Okay. Yeah. Okay, if you have more questions, we left to Wednesday. We can discuss again. Please